Hello everyone. In the last video, we talked about how to get the atoms outside a target, and then use the laser to ionize the atoms and become ions. So it gets many ions moving towards one direction. And then if we just have a cloud of ions moving towards the same direction, we cannot use the ions to quantum computing because they are moving and then they just hit the wall. Yep, they just fly in a free space and hit the wall. The time is very short and we cannot do operations like etc. What we need to do is to confine the ions in a small zoom, in a limited zoom. The ions can oscillate in a small area, but it don't have to be static, but it should not just go away and hit the wall. So we need to confine the ions. How to confine the ions? Since the ions have a positive charge. So a very naive and direct idea is to use the electric field, right? If we form electric potential like this, and then, for example, electric field equals 1/2 alpha x squared, it has such a potential, and then the particle, the ion, could be confined at the bottom of this potential. So as the free, if alpha is positive, right? As the free space has 3 dimensions, we can get the potential also in 3 dimensions like this, and then the particle will theoretically be confined in all 3 dimensions. Is that right? It seems to be fantastic, right? But actually it has a very severe problem. As we all know, that according to the Maxwell equation, the divergence of the electric field equals the volume charge density divided by x0, right? And the electric field equals minus gradient phi. So the Laplace operator phi equals minus rho divided by actual 0. And what is this term? It's just alpha plus beta plus gamma, right? That's this term. And then what is the volume charge density of the position of an ion? Since the ion is just in free space, right? It's in free space, so there's no charge in the free space at the point of the ion, right? So we don't count the charge of the ion itself when we deal with the force on the ion. So this equals 0. If you want to confine the ion, the alpha must be positive. If it is negative, there will be a repelling force and repels the ion away. So in order to trap the ion in all 3 dimensions, we have to alpha, beta, gamma should all be positive. However, the sum of these 3 is 0, so they cannot be all positive. So this is a paradox. It means that, what does it mean? It means that we cannot use a static electric field to confine an ion in all 3 dimensions. So how can we confine the ion? Does it mean that we cannot confine the ion in all 3 dimensions in a limited zoom? Actually not. We have some other ways to confine the ion. And typically there are two main methods to confine. One is to use a magnetic field. One is to use a magnetic field to confine. And the other is to use an alternating time-varying electric field to confine them in other dimensions. Maybe you just if you just use a static field, we can confine the atom in 1 or 2 dimensions, but repel in the other dimensions, right? Repel in other dimensions. So in order to confine in 3 dimensions, there are many 2 ways. Yeah, if using the magnetic field, it's called penning trap. It's a kind of ion trap. And if you use an alternating electric field, it's called Paul trap. And these are two main forms of the ion trap. My roommate came back to the dormitory just now, so I just changed another place to continue the video. Okay, that's no problem. And in this video, I will explain the penning trap, and in the next video, I'd like to explain Paul trap. Okay, so now we will see how the ion move inside the penning trap. So in the penning trap, in both penning trap and Paul trap, people usually use the electric field to confine the z direction. We just confine it in one single direction, which we call the axial direction. And as for x and y direction, the static electric field repels the ions out. Okay, and typically we design the static electric potential as this way, so that in z direction the coefficient is positive and it can confine the ion, and for x and y direction, which we call radial directions, the static field repels the atoms out. Okay, so we have to use the magnetic field to confine the ions in the x and y directions, and similarly in the Paul trap we have the alternating, the time-varying electric field to confine them in the x and y directions. Okay. And as for penning trap, we typically set the magnetic field parallel towards the z direction. And so if we don't have the electric field in the x and y direction, and then in the xy plane, for example, we draw this, and if the B pair is here, if we don't have other forces in the xy plane, and in the xy plane, it just rotates, the animal just rotates around the B field, right? And the trajectory in the xy plane is just a circle. However, we have a repelling force generated by the static electric field, which we have no way to avoid. Yeah, so we have to analyze the movement under both the magnetic field and this repelling static field, and later we will see that it just the ion will still rotate around the z axis in the z direction, rotate around the z axis, but just have some small cycling, small cyclings. Okay, small cycling circles, small circles. Let's do it. So in the Newton's second law, we have this, right? This equals the force on the ion. Since the ion has one positive charge, it's just this way, right? And then we can see what is the electric field. The electric field is minus gradient of the potential, and we just get the minus gradient of the potential. Minus 2x, x, minus 2y, y, 4z, z, right? And then equals v2x, x, 2y, y, minus 4z, z. Okay, and then what is the velocity cross product? The magnetic field is just x, y, z, x, and 0, 0, b 0, right? And we can get it b 0, y, and minus b 0, x, y. Okay, so and then we can have we can calculate this, and that is we can write it down, write this equation down, expand this equation. towards the three axes, three coordinate axes. And we have this EV2x plus 2yy minus 4zz EB0 x. And also for this equation, for every single axis in this equation would be correct. So we can have three equations in each axis. In the x direction, we can just divide m here. And in the x direction, we have we just move everything to the left. In the x direction, we have this equals 0. In the y direction, similarly, we move it to the left. And this is x. And in the z direction, it is relatively simple. And this is the equation satisfied in all three in three directions. As for the z direction, it's very simple. It's just a periodic oscillation, and you can just use cosine to describe. So in the z direction, also we call the axial direction. It's just like this kind of oscillation. I use cosine to describe it. However, in the xy direction, they are coupled, not coupled together. They are coupled together. Just the radial direction, and if we calculate, if we solve this equation, we can get a trajectory like this. Yeah, it's just like it's a large circle, but there are some smaller circles. Yeah, and this is the direction, trajectory of it. And yes, and here it is. So we have already get the basic form of we have calculated how the ions move, and we can see that in z direction, it just moves in this range, and in xy direction, it's moving in this range, and it will not go away. And we can just use so we can use the static electric field and the static magnetic field to confine the ions. And as for this, the big circle is just induced by the magnetic field. It's called magnetron. And as for the smaller circles is called cyclotron. It's just some small cycles. Yeah. So in this video, we have explained how to use how to trap the ions through the penning trap. Yeah, and then in the next video we'll talk about the Paul trap. Okay, yeah, thank you very much.